An intermediate bulk container, IBC, is a container used for transport and storage of fluids and bulk materials. IBCs have become widely used in the industry as they can transport and store more material in the same area than cylindrically shaped containers, reduce manual handling, and are more resistant to weathering. However, some IBCs have been involved in incidents such as stack collapse, ignition of contents due to static electricity, and leakage leading to serious fires or risks to the environment. This film is designed to promote safe practice in the solvent supply chain and protection for all involved. SIA and ESIG are providing this overview of the use of IBCs to increase awareness among solvent users. This guidance should not be used in isolation, and reference should be made to other standards and codes of practice. IBCs are a form of packaging designed for mechanical handling. They're subject to the internationally agreed UN certification procedure, the details of which may be found in the European Agreement concerning the International Carriage of Dangerous Goods, ADR, which regulates the carriage of dangerous goods by road. The IMDG shipping regulations are also based on UN, but have different criteria due to the increased risk when transported by ship. Various UN-certified IBCs are available. For flammable solvents, these can be subdivided into two main types: all metal, either stainless steel or mild steel, and plastic composite. A composite IBC has a rigid outer structure encasing a plastic inner receptacle or bottle, usually made of high-density polyethylene. The outer and inner assemblies are used as an integrated single unit. It has the following components: a built-in pallet of metal, wood or plastic, a plastic outlet valve, usually a butterfly or a ball valve, with a secondary closure cap and possibly a flap to protect the valve, a top filling opening with possibly a venting screw cap. Electrostatic protected composite IBCs can have a combination of dissipative or a conductive outer layer, a conductive grid with a mesh size not bigger than 100 centimeters squared, and a metal contact surface inside the IBC in the form of a pin, a plate, or a ring which penetrates outwards through the plastic body and connects with the metal construction of the IBC via an earthing cable. These measures prevent the build-up of static electricity from brush discharges and from the filling and discharge processes, so that a dangerous static electricity discharge is eliminated. For sensitive products, an additional chemical barrier, ethylene vinyl alcohol. EVOH, or fluorination, can be used to prevent the permeation of solvents or gases like oxygen, carbon dioxide, nitrogen and odors. An additional UV and light protection can be used for products sensitive to light. IBCs used for food products must comply with the applicable legislation. Composite IBCs have been shown to be vulnerable. When exposed to the heat of a fire, plastic or composite IBCs can soften and fail catastrophically, releasing their contents rapidly. The presence of a metal cladding can delay the process, but ultimately all contents may be released. In a fire, the total loss of the contents could overflow the storage area containment. All IBCs, even metal, can have exposed plastic components that are vulnerable to fire. Such ignitions develop rapidly to cause complete failure of the IBC. In a fire, metal packaging may fail hydraulically or by ullage space explosion. When dealing with potentially explosive atmospheres, it is crucial to avoid the accumulation and discharge of static electricity. Electrostatic charging is greatest when liquids are flowing, so it is important to have safe methods of filling and discharging. The operator must ensure that containment is not breached. The selection of an IBC is based on its specification, its condition, its compatibility, its durability, and its suitability for a specific solvent. The IBC must be approved by the IBC manufacturer for the particular solvent. Manufacturers' recommendations and conditions attached to the IBC's UN certificate must be followed and local industry guidance assessed. Composite IBCs may not be compatible with all solvents or acceptable by customers or insurers. The manufacturer will give advice on the compatibility of the bottle and its accessories, valves, valve seals with the intended use. If there is no approval, do not use. There is a legal requirement in the transport regulations that permeation shall not create a danger under normal conditions of transport. An IBC with a metal pallet base has a longer resistance to fire and may delay structural failure. Some solvents and pure hydrocarbons have a low conductivity and hence present a significantly greater static risk than others, as there can be a buildup of static charge which can spark a fire or an explosion. To eliminate this hazard, the operator can either use a metal IBC or an electrostatic protected composite IBC in combination with a suitable earthing system when filling or emptying. If an electrostatic unprotected composite IBC is used, the flash point of the solvent needs to be higher than the ambient temperature by enough margin to prevent a flammable atmosphere. The maximum ambient temperature and the safety margin can vary from country to country, and so local codes of practice should be used. If a lower flash solvent is to be put in an IBC, an electrostatic protected composite or metal IBC must be used, which prevents electrostatic discharges from inside and outside of the IBC. Many electrostatic protected IBCs meet these criteria and can be used for low flash solvents provided earth protection is proven. Its static discharge via the pin and earthing cable must be in good working order. Though there are some exceptions, such as for some acetates, oxygenated solvents generally have a higher electrical conductivity and much lower static buildup, and so lower flash points can be tolerated. When handling very low flash point oxygenates, the operator has to make a judgment between the risk that flammable vapor is always present and the reduced risk of ignition due to the high conductivity of the product and the use of an electrostatic protected composite IBC. To identify the acceptable minimum flash point of a hydrocarbon or an oxygenated solvent to be put into an electrostatic protected IBC, the risk assessment will take into account the manufacturer's recommendations and the effectiveness of the static removal and earthproofing systems across the whole supply chain. If there is any doubt, it should be noted that a metal IBC is inherently more conductive than an electrostatic protected composite IBC. The normal earthing point on a metal IBC is its frame. Metal IBCs must be earth bonded to the frame. The operator has to decide whether to buy new, reuse, or buy previously used IBCs. The test report and UN approval will enable a check on the design of frame and bottle, closure, valves, make and type. If the decision is to buy previously used for dangerous goods, there should be evidence that it has been suitably configured, has a known history, and has the required UN certification. If there are any doubts, or there is an incomplete history, then previously used IBCs should not be used for flammable materials. Before filling, there must be a formal inspection to ensure the IBC is fit for purpose and prepared. Damaged pallet corners on composite IBCs can snag and tear the bottles of adjacent IBCs. IBCs shall be labelled in compliance with supply and transport regulations. The IBC and the filling equipment, such as fill nozzle and hoses, must be bonded and earthed prior to filling to prevent static charge buildup and must be designed for flammable service. Splash filling of flammable liquids is dangerous as it creates static and must be avoided either by bottom filling at not more than 2 meters per second or by using a metal conductive fill nozzle or dip pipe, which must reach to the base of the IBC, and the maximum filling velocity must initially be limited to 1 meter per second. Once the end of the filling pipe is covered, the maximum filling velocity must be limited to 2 meters per second, giving an industry-typical filling time of 6 to 10 minutes. After filling, the earth connection should be left in place for the relaxation time, as advised by the product supplier and IBC manufacturer, to allow static charge to dissipate. It must be emphasized that splash filling and uncontrolled gravity filling of solvents into IBCs are not safe practices. Measures should be taken to prevent overfilling, such as metering, weigh scales, or high-level detection and cutout. A local exhaust ventilation system to remove vapors generated during filling operations should be available to reduce risks of ignition and exposure to operators. Uncontrolled filling of IBCs at a customer's premises must not occur. The risk of overfill, rupture, or static discharge is high. IBCs should be returned to the supplier for filling. The only exception is a fixed filling installation and the supplier's safety audit confirming appropriate safeguards are in place. At the customer's premises, IBCs must be correctly earthed before discharge and kept away from any sources of ignition. All IBCs must be inspected before use and retested regularly. A competent person must examine each IBC at prescribed intervals in order that UN certification can be maintained. Routine inspection, maintenance and repairs must be carried out in accordance with ADR and manufacturers' recommendations by competent organizations. IBCs must be clean and vapor-free, as verified by a portable gas detector to reduce the risk of a fire. IBCs have the potential to fail catastrophically during pressure testing for leaks. Therefore, safety precautions must be taken. Modifications to IBCs must be carried out by the IBC manufacturer. Leaking packages must be identified and rectified promptly in a safe area before a significant pool can accumulate. Ideally, flammable liquids, including solvents, should be stored in a cool, dry place in the open air, away from sources of ignition and heat. Outdoor storage has disadvantages such as ultraviolet light degradation of plastic packages, damage by wind and rain, and solar gain, causing the packages to heat up. Lightweight weather protection and good stock rotation minimize these disadvantages. Steel drums containing flammable liquids should be kept away from composite IBCs where practicable. For indoor storage, ventilation is important, and the hazardous areas assessment must consider the wider range of ignition sources. The risk assessment for the site should reflect the fact that a fire in an IBC store can result in the release of all the liquid within a period of 10 minutes. Specialized advice may be required in the selection and deployment of fire detection systems and firefighting equipment. Flammable solvents should be segregated from products such as oxidizers and other reactive products and from combustible liquids that will increase the fire loading. Pool fires that run under pallets of metal drums or metal IBCs will escalate the incident, increasing the risk of boiling liquid expanding vapor explosion leading to projectiles. The risk may be reduced by separating plastic and composite IBCs from metal drums and metal IBCs. Segregation could include curbs or level grading to control the flow of burning liquid. If limited bunding is provided, the effects of liquid flowing out of the bund should be considered. To reduce risks, the quantity of liquid stored in IBCs should be minimized and suitable selection of lift trucks, store location, bunding and storage racks be considered. Any lift truck used to handle IBCs containing highly flammable liquids should be suitable for use in zoned areas. IBCs may be stacked, but there are limitations in load-bearing capacity as labelled under ADR and differences in design. A competent person should draw up site rules and procedures to ensure that IBCs are stacked safely. Filled IBCs that are designed to stack together should be stacked no more than 2 high and only on level ground. Partly filled IBCs should be treated as full IBCs for stacking height. Drums should never be stacked on IBCs. Racking systems allow high space utilization and must be competently designed, installed, and subject to adequate inspection and maintenance. Racking systems are prone to mechanical damage by lift trucks and corrosion. Containment systems such as yards, bunds, drains, interceptors, and their control valves should be designed, inspected, and maintained to minimize the potential impact of product leaks. Good housekeeping regimes must be implemented to prevent buildup of combustible materials, spillages, and vegetation. The operator will need to consider site security and, where appropriate, the specific provisions in ADR. Safety should be actively managed through a process that starts with risk assessment. The findings of risk assessments must be communicated to employees and should underpin operating procedures. Regular training should include solvents properties and hazards, procedures for safe handling, use of lift trucks, racking and stacking, recognition of abnormal situations, reporting of faults and incidents, use of protective clothing, housekeeping, dealing with minor leaks and spills, and emergency procedures. IBCs have become very widely used in the solvents industry, and it is important that they are used safely. The solvents industry is well regulated, and there is information and advice to ensure the risks associated with solvents can be minimized, including our recent films about the safe handling of solvents and static electricity. We acknowledge the contribution from the Chemical Business Association and the UK Health and Safety Executive in the production of this film. Thank you for watching, and if you need more information, please view our comprehensive websites.